Okay, so let's have example 2, RLC simple circuit. So the given is we have four components here: a 2 Henry inductor, 4 farad capacitor, 6 Henry inductor, and an 8 ohms resistor. So taking the Laplace equivalent of the circuit, of course we're going to have 2s here, then 1 over 4s, 6s, and 8 here. Okay, and the corresponding labels of VIS, VRS, and IS. So to solve for the transfer function, we start once more by KVL, and for our given circuit, then we're going to have VI of S to be equal to 2S plus, that is summation of the impedances, okay, plus 6S plus 8, and that would be multiplied to IS, okay. And we know by Ohm's law that IS is equivalent to VRS over 8. Okay, so we take this equation because we are interested to incorporate VR of S in our equation because it's the output. So simplifying, substituting this IS to our first equation and simplifying things, so we're going to have VI of S to be equal to, we could have here, combining the two similar values, we have 8s plus 1 over 4s plus 8 multiplied by VR of S over 8. And simplifying further, we're going to have, say, VI of S equal to, uh, we're going to have, we multiply 1 over 8 with this equation, and at the same time adding the fractions now with the whole numbers. We're going to have 32s squared, okay, plus 32s plus 1, or all over 32s, okay. That's VR of S. And solving for output, VRS over input, VIS. So we're going to have 32s over 32s squared plus 32s plus 1. And that's already our transfer function. We could also express this transfer function in terms of uh, this one. No? So we're dividing the whole equation by 32 over 32. So we're going to have s over s squared plus 32, sorry, that would be s only plus 1 over 32. Okay, so that is now our transfer function. Okay, for the same problem, no, RLC circuit, our example 2, let us solve the state space model. So first, we're going to identify our state variable, and of course the same state variables, let us use the same state variables to be Q of t and I of t. And solving for the state equations, that is the derivative of qt, first derivative of qt and first derivative of it. Okay, so we get this state equation from our circuit, no, the KVL. So by KVL, Kirchhoff's voltage law, we will get VI of T to be equal to, uh, let's combine already the two uh, inductors. So that we're going to have 8 di over dt, plus for the capacitor, we're going to have 1 over 4 integral of I dt. And then for our resistor, we're going to have 8 I of t. Okay. Now, of course, we are interested to get the equation of di over dt. So, solving for di over dt, we're going to have 1. This we know already that the integral of I dt is equal to q of t. So that will be 1 over 4 multiplied by 8, no, the coefficient of dt. So we're going to have negative 1 over 32 q of t. Okay. And then we are going to have here 8 I of t divided by 8, the coefficient of the I dt. So we're going to have negative I of t. And of course, we have our input, positive vi of t. Okay, so that is the equation of di dt, and we know already that dq over dt is equivalent to I of t. Just to complete the equation, so we know already that that is equivalent to 0 qt and also 0 vi t. Okay, now writing the simultaneous equations, we represent solution. Let's have your solution of two simultaneous equations, and we're going to write that in vector matrix form. So we let x1 to be our q of t, and then x2 to be the I of t, and of course x1 dot, or the first derivative, is dq over dt, and the x2 dot is the di over the dt. Okay, let us also identify already that let's assign u to be our input VIT, and let's assign y, these are just notation, to be the output, which is the VR of t. And therefore, expressing our state equation in vector matrix form, a solution of the two simultaneous equation, then we're going to have x1 dot, x2, or rather x1 dot is equals to 0x1 plus x2 plus 0 u. And then for x2 dot, that would be equal to negative 1 over 32 x1 minus x2 plus u. Okay, so that is our solution, to simultaneous equations. For the output, okay, solving for the output equation, since we know that our output y is equals to the voltage drop at the resistor, and by Ohm's law, we know that the resistor is simply equals to its impedance times the current flowing through it. Okay, So therefore, our output y is equals to, if we could complete it, we know that I of t is equals to x2. Therefore, this is 0 x1 plus 8 x2 plus 0 input u. And therefore, our state space equation in vector matrix form would be x1 dot x2 dot will be equal to 0 1 negative 1 over 32 negative 1. Okay, that is x1 x2 plus the matrix 0 and our okay, so we lack 1 over 8 here, no? 1 over 8, we should have 1 over 8 here because of the coefficient of didt to be transposed on the other side, so we should have 1 over 8 here. And so here we should have 1 over 8 here also. Okay, and therefore we should have 1 over 8 here. Okay, that is the u. And for the output equation y, we should have 0 and 8. That's x1 x2. Okay, so we don't have a d here, so there's 0 output. So therefore our state space equation is this one. Okay. Okay, so let's now try to convert the transfer function that we have derived to the state space equations. So we start with, of course, the transfer function that we have derived, and as we know already, we need to subdivide the transfer function into two subsystems. So starting with the first subsystem, uh, that the transfer function would be x1 of s over vi of s to be equal to 1 over s squared plus s plus 1 over 32. And then cross multiplying, we're going to have s squared plus s plus 1 over 32 x1 of s will be equal to vi of s. The next thing is to take the inverse Laplace of this. So inverse of s squared x1 of s will be second derivative, no? So that will be 2 dots, no? x1 of t, okay, plus s x1 s x1s will be first derivative, so x1 dot of t, and of course the 1 over 32 x1 of t, and on the other side of the equation that will be vi of t. And as we know already, the equivalent says the equivalent of x1 double dot is equal to x2 dot of t, and x1 dot is equivalent to x2 of t, and of course the 1 over 32 x1 of t. And we know already from the previous slide that vi of t, we use the notation u, no, for the output. Okay, so we express now our equation, no, the x2 dot, now dropping the t, okay, for a simplified format. So x2 dot will now be equal to negative 1 over 32 x1 minus x2 plus u. Okay, and as we know already that x1 dot is equivalent to x2. Okay, just but to complete the equation, we know that it's equivalent to 0, x1, and 0, u. Okay, so we already have our state equations. At stage 2, no, on the second stage, okay, so say let's write this as um, at stage 1, and then here let's have at stage 2. Okay, okay, so at stage 2, our transfer function would be VR of S over x1 of S to be equal to S over 1, which will be equivalent to uh, Sx1 S equal to VR of S. And of course, taking the inverse Laplace of this, where S means first derivative, so that will be x1 dot of t equals to VR of t, or that is written as VR of t. And from here, we know that our y, no, we use the notation y as for the output, is equivalent to VR of t, which we have derived as x1 dot of t. And x1 dot of t is equivalent to x2 of t. Okay, so for a simplified version of y, we could write it as 0 x1 plus x2 plus 0 u. Okay, so that is now the equation. So our state space equation is now in vector matrix form, could be written as x1 dot x2 dot is equal to 0, 1, negative 1 over 32, negative 1. So x1, x2 plus 0, 1, u. And then the output equation to be 0, 1, x1, x2, and 0d. So we don't have another term for the output. So therefore, this is our state equation. Now, if you notice, again, there is a slight difference from the state space that we have derived earlier. And the difference is in the derived state space equation, we have here 1, 8, and we have here 8. Okay? And later on, we will see that this state space equation is still the same, no, as the one. Okay, so let's have the right spelling here, equation. Okay, now let's convert state space to transfer function. Let's start with the derived state space equation, wherein the b is 1, 8. Now, Please note that this matrix is again, this is A, and this matrix is B, this matrix is C, and we don't have D here, so it means that the D matrix is equals to 0. Okay, and to start our uh, the process of solving this, we should recall that the standard equation or notation for our transfer function, we need to derive the ys over the us with this formula. No? The c multiplied by the x of s times b plus d, where x of s is equivalent to the si, no, identity matrix minus a inverse. Okay, and so our si minus a is equivalent to, that is the si for a 2 by 2 matrix, because our a is a 2 by 2, so that will be s0 and then 0 s minus the matrix a, which is 0 1, negative 1 over 32 minus 1, and that will give us s minus 0 to be s, and then 0 minus 1 to be negative 1, and then 0 minus negative 32, so that would be positive 1 over 32, and then s minus negative 1, so that will be s plus 1. So this will be our si minus a matrix. Now, taking the inverse of this, we know already the formula, the si minus a inverse is equals to adjoint of the matrix over the determinants of this matrix. So I would like to write immediately the answer. So for our numerator, the adjoint would be, no, mag-interchange itong diagonal, itong s at saka s plus 1 is mag-interchange. So we're going to have here s plus 1, and then we're going to have here s, and then the sign of this and this will reverse. So the negative 1 will be positive 1, and the positive 1 over 32 will be negative 1 over 32. That is for the numerator. And for the denominator is the determinant of this. So that will be s times s plus 1. So we're going to have s squared plus s minus negative 1 times negative 32. So that will be positive 1 over 32. Or right away, that is 1 over 32. And then we will substitute this to our equation, this one. So we're going to have y of s over u of s is equal to matrix C 0, 8 multiplied by xs, which is this is what we have derived. So that will be s plus 1, 1, and then negative 1 over 32, and then s, that will be all over s squared plus s plus 1 over 32. Multiply here the matrix B, which is 0 and 1, 8 elements. Now, note here that D is 0, so supposedly we still have here plus D, but it's 0. Okay, so we only have this term na lang. So, simplifying, all we need to do is just to simplify. So this 0 times this is 0 plus this times this, 8 times negative 1 over 32. So that is 8 over negative 32. No, so that will be negative 1 over 4. So that's the first element. And then 0 times 1 plus 8 times s. So that will be 8s. Okay? And then multiplied again by 0 and 1 8. 1 8. Okay? Over s squared plus s plus 1 over 32. Okay? So we multiply this. Negative 1/4 times 0 is 0. And then 8s times 1 over 8 is s na lang. So therefore, our final answer, ys over us, will be equal to s over s squared plus s plus 1 over 32. So we have arrived at our correct transfer function. Now lastly, let's discuss converting state space to transfer function. This time, the converted state space. No? So, again, the difference is only the value here, which is 1. Kanina kasi it's 1/8. And dito naman, 1. Kanina kasi it's 8. So, once more, the standard formula for converting is ys over us, which is equals to c times xs times b plus d. Now, these are matrices, no, take note. And as we have solved already the x of s to be the inverse of the matrix Si minus A, and we have solved it already to be this, no, s plus 1, 1, negative 1 over 32, s all over s squared plus s plus 1 over 32. So all we have to do now is to simply substitute all the matrices to our standard conversion formula. So C here will be 0, 1, and then our XS here, we copy everything, S plus 1, 1, negative 1 over 32, S, and then the B, which is 0 and 1, and the denominator, which is s squared plus s plus 1 over 32. Now, you don't need to write here the d, it's understood, but just to emphasize, meron pa tayong plus d dito, no, na plus d. Now, kapag hindi kasi 0, no, I just want to emphasize that kapag may value to, hindi to 0, kailangan pa natin itong i-combine, no, i-simplify. Just what we have done in example 1, no, may value na 1 dito. Okay, now in this case, that's 0. So, mas madali ito ngayon i-simplify. So, all we have to do next na lang is to simplify. So, multiplying these two matrices, 0 times this is 0 plus 1 times this is negative 1 over 32. First element of the matrix, another element of the matrix will be 0 times 1 is 0 plus 1 times s is s. So, we have here s, and then the matrix 0, 1 over our denominator s squared plus s plus 1 over 32. And of course, our final answer, the transfer function, will now be multiply this with 0 is 0 plus s times 1 is s. So we have here s over s squared plus s plus 1 over 32. So this is now our transfer function. Okay, so we also arrived to our correct transfer function.